In this unit, we are going to see some examples of how to solve linear equation systems using the Gauss method. We are going to see an example to remember the Gauss method, and then we will see a couple of examples where we solve linear equation systems using the Gauss method, but where all the coefficients of the system are not known. That is, they have parameters. For this, we will remember what is a linear equation system and how to apply the Gauss method to solve them. So, first of all, if I want to solve this linear equation system that you have on the screen, the Gauss method tells us that we write that system in this way. That is the first equation, x plus y plus z equals 6, only the coefficients. The second equation, x minus y minus z equals minus 4, also only the coefficients, remembering that the x below the x below the x, and the z below the z, and then the independent terms in the third equation. And then what we have to do are operations, equivalence transformations, that make zeros between the coefficients, that is zeros below this line, a 0 here, a 0 here, and a 0 here, a 0 here. What operations can we perform? Well, those that are allowed, that is to say, to an equation I subtract another one multiplied by a number, to an equation I divide it by a number, etc., etc., as long as I neither multiply nor divide by 0. So in this case, for example, if the equation 2 subtracts the equation 1, I will have a 0 here, which is what we are looking for, and if the equation 3 subtracts the equation 1 multiplied by 3, I will have a 0 here, which is the other 0 that we are initially looking for. Well, let's do these operations. 1 minus 1, 0, minus 1, minus 1, minus 2, minus 1, minus 1, minus 2, and minus 4, minus 6, minus 10. I already have the second equation. I do the corresponding operations to the third, and I obtain the third equation. Well, we already have those two zeros. What do we have left? This 0 here to make zeros below that line. This minus 2, we have to convert it into a 0, doing that type of operations. So if I subtract to the equation 3, the equation 2, I will have that 0 directly. We do that operation in this case. In addition, we get all zeros. Once we have reached 0 below this line, 0, 0, and 0, what we do is write it back as a system of equations. For example, the first equation would be this one here. The new first equation, in this case, coincides with the previous one. The second equation would be this one here. The second one, this one is a new equation. And the third one, so that the system is x plus y plus z equals 6 minus 2 and minus 2z equals minus 10. Let's remember this system, it is equivalent to this system here, so both have the same solutions. And this system, we already know how to solve it. What can we say about it? Well, that it is a consistent, indeterminate system whose general solution is this way. That is, we choose one of this equation, we choose y or z as a parameter. For example, I have chosen z equals alpha, where alpha is a real number of any, and solving y is worth 5 minus alpha. Substituting the first equation, y is equal to 5 minus alpha, and z is equal to alpha, it turns out that x is worth 1. Then, as we can see, it is a consistent indeterminate system with infinite solutions given to each of them for each of the values of alpha. This system has 1 degree of freedom. Well, this is the way to apply the Gauss method to a linear equation system. What happens when all the coefficients are not known? For example, z here, x minus z equals minus 2, 2z plus 4z equals a, x plus z equals 1. In this case, this independent term is known to us, and this coefficient neither. The unknowns are still the same, x, y, and z, and we know that a is not an unknown because the text tells it to solve the following system of linear equations according to the parameters of the parameter a. Then we know that a is not an unknown. Well, we will apply the Gauss method as before. We write the equations, the first equation, the second equation, the third equation, by setting the appropriate parameters. If it is an a, then it is an a. If it is not an a, then it is a 0. And the independent term is an a, then it is an a. And we will apply it the same. We will do zeros under this line. That is a 0 here and a 0 here. To do a 0 here, first operation, equation 3 minus equation 1, 1 minus 1, 0, 1 minus minus 1, 2, and a, plus 1 is left here, and 1 plus 2, 3. Since we do not know the value of a, then it remains as a plus 1. The following, if we are going to do more zeros under this line, we have this 2, equation 3 minus equation 2, and it will give me that 0, with which we arrive at this system. Once we have reached 0 under this line, remember that we passed it to the equation system. First equation, second equation, and third equation. This system, as we have said, is equivalent to the previous one, and now the third equation is the one that will determine what type of system we have. So the first thing we see is that if the a is worth 3, this here would be 0, and this would be 0, it would have 0 equal to 0. This equation would disappear, and it would have only the first two. Then it is a consistent indeterminated system, in this case, whose solution is, well, the y or the z as a parameter. I have chosen z equals alpha. Then, by solving the y, it is worth 3, since the a is worth 3, minus 4 alpha divided by 2. And replacing the first one, I have that x is equal to minus 1 minus 2 alpha divided by 2. As you can see, if a is worth 3, the system is consistent indeterminated, with infinite solutions given by this expression for each of the values of alpha belonging to R, which is the only degree of freedom of the system in this case. What happens if a is different from 3? Well, if it is different from 3, as this number is not 0, it can go dividing to the other side, with which I have that the system is consistent determined with a single solution. What is the solution? Well, if I pass this by dividing, I have that z is worth minus 1. Substituting the second equation, I have that y is worth a plus 4 divided by 2, since I do not know what does a worth. And replacing the first one, I would have that x is equal to a minus 2 divided by 2. As you can see, the system is consistent and determined with a single solution. Well, this happens, as you can see, it works exactly the same, although the a was a well-known number, and the only thing to be careful is not to multiply or divide by 0. Let's see this other example. If the system x plus a times y minus 3z is equal to 1, y minus 3z is equal to a, and x plus y plus 2z is equal to a, well, again, we apply the Gauss method. Equation 1, equation 2, equation 3, x below x, z, etc., etc., and putting the parameters where they correspond. We do zeros under this line, a 0 here and a 0 here. First operation, equation 3 minus equation 1, gives me a 0 here and puts me here a 1 minus a. If we continue with the Gauss method, the next one is to do 0 to do 0, this 1 minus a. How can we do it? Well, in a simple way, if the equation 3, I subtract the equation 2 multiplied by 1 minus a, it would already have 0. That is, to the equation 3, I subtract 1 minus a by the equation 2, and I get that 0. Of course, I will always be able to do that when the a is different from 1, because if it is equal to 1, I already have the 0 there, it is over. Therefore, here we have to separate two cases. If the a is worth 1, I have finished here, because since I already have the 3 zeros that I was looking for, and if the a is different from 1, then I would have to do that operation to get that 0 there. Well, we have to analyze the two cases separately. Since we do not know the value of a, then depending on the value of a, it will have one situation or another. Let's analyze the first case, a different of 1. In that case, once I have arrived here, I write it again as a system, x plus a times y minus 3z equals to 1, y minus 3z equals to a, and 8 minus 3 times a times z equals to the square a minus 1. This equation, as before, is going to determine what type of system I have, always within the case of a different from 1. So what disjunctive do we have in this case? Well, that the a is worth 8/3 or not. If the a is worth 8/3, as you can see, it is different from 1. If the a is worth 8/3, this here is 0. Then I would have 0 equal, substituting here 8/3 minus 1, I have 55 divided by 9. I have 0 equal to 55 divided by 9. That can never happen. Therefore, in that case, we have an inconsistent system. The system does not have a solution. When the a is worth 8/3, the system is inconsistent. What happens if a is different from 8/3 and also different from 1? Remember that we are in that case. Well then, the system is consistent and determined, since this can happen by dividing. I divide and I would have that z equals to a square minus 1 divided by 8 minus 3 times a. Substituting in the second equation, I would have the y, and substituting in the first, I would have the x. Then, in the case of different 8/3, the system is consistent and determined with a single solution given by this expression here. And now we have to analyze the case to be equal to 1. What happens if a is equal to 1? Remember, we had reached here and we would have the 0 here. If we transform this into a system that has this 5 times c equals to 0, that can only have a solution if z is equal to 0. Then, the system in this case is consistent and determined. And the only solution is z equals to 0, y equal to 1, and x equals to 0, substituting in the corresponding equations. Then, as you can see in this case, we don't have to forget it, because this gives us a new case, which may be included in the previous one. But as we don't know, we have to treat it separately. Then, in this case, we have seen how to solve linear equation systems with and without parameters, using the Gauss method. And we have to remember that we cannot multiply or divide by 0 when we do the operations, the corresponding equivalence transformations.